Okay, hopefully the quiz was okay. I hope you benefited from the extra 5 minutes, the 35 instead of the 30 minutes. So a couple announcements, and we'll try to get the quiz graded as quickly as possible, hopefully by the end of the week, but no guarantees. So homework 7 is going to come out later this week, by Thursday probably. It'll probably only be, it'll be max 3 questions. Okay, just because it'll be on the topics we covered today and Thursday, but which isn't really sufficient time to do an entire homework. But I didn't want to go 2 weeks without a homework, so it'll be pretty short, and it'll be due this Sunday, and it'll probably come out in the next day or two. Okay, and then as I mentioned before, now that we're 4 out of 5 quizzes in, I'll start to consolidate everyone's grades once quiz 4 is graded and try and figure out how many points you need in order to pass the class. Okay, with that being said, the passing threshold will likely change. I think I'm going to make it that you need 80 points to pass instead of 75. Okay, nobody believe that. It's probably going to be moved to 65-ish. Yeah, I wouldn't do that. Okay. Yeah. So 65 is what I'm looking at. I can't make it any. You knew that was a lie. Okay. And also, make sure you read the Binomial Theorem note on the website, because that covers 90% of what we're going to do today and Thursday, but there are also some examples that we'll do in lecture that aren't directly in the notes. But I think that note walks through most of it. Any questions logistically? Cool. So let's get into the Binomial Theorem, and also this sort of starts the last unit, if you will, of the class. So our final quiz, which I think is during the last week of classes, will be on everything that we see from now until that point. So before we get into what a binomial is, into the binomial theorem, we should say what a binomial is. And it's just a polynomial with 2 terms joined by addition. Right? And terms are just different things joined by addition. And it could be of multiple variables. Right? So for example, a plus b is a binomial with 2 variables, a and b. And when you multiply out something like a plus b times c plus d, what you do is multiply every term in the first parentheses by every term in the second parentheses. Is that clear? For each term in the first bracket, so for example, a, we multiply it by every other term in the second bracket. So that's why we have AC, AD, right? And then BC and BD. Okay, pretty straightforward. And so we do a similar thing when we multiply equal binomials, right? So a plus b and c plus d, sure, there are 2 different binomials. But now if we look at the product of x plus y and x plus y, we do the exact same thing, right? So we have xx, xy, yx, and yy. And that's what we get. And we can combine like terms to get this thing that we've probably seen before, x squared plus 2xy plus y squared. Any questions so far? Okay. And to get you to start thinking about where we're headed, notice the coefficients on this are 1, 2, and 1. Where did we see that before? Pascal's triangle, right? And so that's where we're headed. So notice, for every term in the expansion of x plus y quantity squared, we choose some number of x's and some number of y's to multiply together. Is that clear? Each of these terms involves a product of some number of x's and some number of y's. Okay? And notice, since we will have 2 brackets, the total number of things we multiply together will be 2. Is that clear? Okay? And so we can think of it in terms of choosing how many x's are in our product or choosing how many y's are in our product. And note, Pascal's triangle is symmetric, so it doesn't really matter. If we choose, for example, 1x, we will choose 2 minus 1 y's. If we choose 0 x's, we'll choose 2 minus 0 y's. Okay? So there's 3 cases we can look at. Either we choose 2 x's and 0 y's, so 2 choose 0, right? Which tells us what the coefficient on x squared will be, right? Because that's the number of ways to choose 2 x's and 0 y's. Or we could choose 1 x and 1 y, so it's 1 x, 1 y, times the number of ways we can make that happen, which is 2 choose 1. Or we could choose 0 x's and 2 y's, which would give us y squared, times the number of ways we can make that happen, which is 2 choose 2. Right? We have 2 choose 0 terms of the form x squared, 2 choose 1 terms of the form x times y, and 2 choose 2 terms of the form y squared. So it tells you the expansion of x plus y quantity squared is 2 choose 0 x squared plus 2 choose 1 xy plus 2 choose 2 y squared. Any questions with this so far? Okay, and so we can also expand this to x plus y cubed, right? We know each term will either contain 3 x's, 2 x's and 1 y, 1 x and 2 y's, or 0 x's and 3 y's. Is that clear? So our terms will either be of the form x cubed, x squared y, xy squared, or y cubed. Is that clear? How many ways can we choose 3 x's and 0 y's? 3 choose 0, right? How many ways can we choose 2 x's and 1 y? That would be 3 choose 1. And similarly, 3 choose 2 and 3 choose 3. Notice we're choosing the number of y's. Okay, so this gives us, it implies that the expansion of x plus y cubed is 3 choose 0 x cubed plus 3 choose 1 x squared y plus 3 choose 2 xy squared plus 3 choose 3 y cubed. Okay, and recall, these are just the numbers from Pascal's triangle, right? In our case, this is 1, 3, 3, and 1, which appears as a third row of Pascal's triangle. Any questions with what we've seen so far? Out of curiosity, how many people have seen the binomial theorem before? Okay, a good number. Okay, so let's formalize it. So the binomial theorem states that the expansion of x plus y to the n is the sum of k going from 0 to n of n choose k, x to the n minus k times y to the k. What we're saying is we're choosing k y's and n minus k x's. And so this is just a formalization of what we just saw. So any questions with this formal definition? Great. And so as an example, suppose we wanted to expand 2a squared minus b to the exponent 5. In this case, we can think of x as being 2a squared and y as being negative b. Okay? Then the expansion of 2a squared to minus b to the 5 would be something like 5 choose 0 x to the 5 plus 5 choose 1 x to the 4y plus 5 choose 2 x cubed y squared plus ... 5 choose 5 y to the 5. Okay, and then every instance of x we replace with 2a squared, and every instance of y we replace with negative b. Okay, and this is more just to illustrate how you would do this if you needed to, but it won't be like, I'm not going to ask you a question, just expand this out, because there's not really much value in doing the arithmetic. You should just know how to do it if you had to. But like, doing all of these random calculations that you'll have to do are not important. And you'll see what I mean by that right now. So x is really 2a squared, so we have 2a squared to the 5. okay? Plus 5 choose 1, 2a squared to the 4 negative b, plus 5 choose 2, 2a squared to the 3 negative b squared, and so on and so forth, right? And we can simplify just a few terms of this just to see what would happen. So what's 5 choose 0? That's 1. What's 2 to the 5? That's 32. A squared to the 5 is just a to the 10. And notice, if y is negative, the term's polarity, if you will, like their positiveness or negativeness, will oscillate, right? It'll go from positive to negative, and so on and so forth. Because here we'll have negative b, but the next term will have negative b squared. So we'll go from negative, positive, so on and so forth. So here we have 5 choose 1, which is 5. Then we have 2 to the 4, which is 16. Then a to the 8, because we have a squared to the 4, times b, but b is negative, so I place that with the minus. And so on and so forth. Okay, and we'd go all the way until we get to negative b to the 5. Okay, and you can replace 16 times 5 with 80, I think. And you could do that. Okay, but again, the process of bashing this out is not that important. You should just know how to do it if you had to. Is that okay? And so what's a little more relevant is this idea of a general term. And this is where you might have to do some calculations. So we defined the kth term in the expansion of a binomial as n choose k, x to the n minus k, y to the k. So this is just looking at one specific term in this expansion. Okay, so the general term is just the kth term, and really the expansion of x plus y to the n is the sum from k0 to n of all the general terms. Is that clear? And so the general term gives us a nice expression to find the term at spot k. But notice we start counting at 0 because, in the expansion of x plus y squared, there were 3 terms. In the expansion of x plus y cubed, there were 4 terms, and so on and so forth. So, and when our exponent is n, we actually have n plus 1 terms where their indexes go from 0 to n. Just like the Pascal's triangle. The very left number in Pascal's triangle of a row is something choose 0. The very right number is something choose n. So it's really the same as there. Okay, so what if we wanted to find the general term of 3a squared minus 2b to the exponent 5? Well, we really just use this expression. And this is something you sort of have to learn. What exactly the general term looks like. And we do some simplifying tricks just so we don't have to do multiple exponentiations at once. Okay, so I plugged x is 3a squared, y is negative 2b into this expression, and then I rewrote 3a squared to the 5 minus k as 3 to the 5 minus k, a to the 2 times 5 minus k, which is really just a to the 10 minus 2k. Move the negative 1 from this term out front, and essentially just made simplifications so that when I need to use this for calculations, it's a little more straightforward. Okay? So any questions with what's going on here? I'm really just plugging in, given some expansion. I use the expression for what the general term looks like, and I do some simplification. But any questions with the general idea? And it'll become a little more clear what the point of this is when we look at a question that uses it. This is sort of just the stuff that we have to get out of the way. Any questions with the general term? Okay. So as an example, let's calculate the general term of x to the 5 minus 1 over x squared. Okay? Really, notice I can write 1 over x squared as x to the negative 2. Right? So this is really x to the 5 minus x to the negative 2 to the 7. And so the general term will be something like 7 choose k, x to the 5 to the 7 minus k, negative x to the negative 2 to the k. Is this clear? And notice, in the example before, we had different bases, right? Like, we didn't know that, like, a and b were probably not equal, so we couldn't combine these two, right? You had to write them as separate products. But here, our base and the exponent is x for both of them, so we can combine it to just have a single x term. So a single x to a single exponent. And we will pretty quickly see why that's useful. So I'm going to write negative x to the negative 2 to the exponent k as negative 1 to the k, x to the negative 2k. Is that clear? And if I pull the negative 1 to the k out front, it'll be immediately obvious whether that term is positive or negative. I just look at k. Right? So negative 1 to the k, 7 choose k, x to the 35 minus 5k, right? Because that's what I get by multiplying 5 by 7 minus k. Then I have x to the negative 2k here. But then I can combine these two x terms because they have the same base. So the general term, in its most simplified form, is something like this. Is that clear? So this is what like if you were asked, I don't know, on homework or on a quiz, or just out in the wild, what's the general term of this? You would provide whoever's asking you that with such an expression. And what's nice about this is, say you want, like, tell me what the exponent on x in the second term of this expansion would be. I just plug in k is equal to 2 here. Is that clear? This is an instant formula. It'll tell me exactly what any term of this expansion is without having to write out the entire expansion. Is that clear? Okay, and again, this will become a little more evident when we look at an example. So basically, what we will do for the remainder of today and a lot of Thursday is just look at different applications and properties of the binomial theorem. Okay? So the first one I want you to play with on your own. What is the sum of the coefficients in the expansion of 3x squared minus 4x to the exponent 12? Okay? And so, let's try it. We write out the expansion. And we know this will look something like 12 choose 0, 3x squared to the 12, plus 12 choose 1, 3x squared to the 11, negative 4x. And just to be a little more explicit, on this term, what would the coefficient be? Well, it would be 3 to the 12. On this term, it would be 12 times 3 to the 11 times negative 4. And you see where I'm going with this. Like, we're not going to sit here and calculate this. So what I want you to do is talk to the people near you and try and determine if there's an easier way to figure out what the sum of the coefficients in this expansion is. So I'll give you a couple minutes to try and figure that out. Okay, Any ideas? What's an easier way to determine the sum of the coefficients in this expansion? Does anyone know what the sum is? Any guesses? It's between 0 and 2. Okay, it's 1, but let's take a look at why it is. And so notice, suppose you were given some very long expression dealing with polynomials. Okay, so let me come up with some example. Pretend we had 3xy to the 15 plus 17 x squared z to the negative 55 minus 13 y to the x. Some expression like this. What I really want, and pretend this was, I don't know, f of x, y, z. And I mean, let's just make sure it's a polynomial. That's right, sure, something like that. And what I really want is the 3 plus the 17. Right? If I want the sum of the coefficients of this thing, I want the 3 plus 17. So how can I get that? What can I plug into the function to get just 3 plus 17? 1, right? You pass in 1 for x, 1 for y, 1 for z, and you just get 3 plus 17, which is 20. So that also applies over here. If you just pass in x being equal to 1, you get 3 minus 4 to the 12, which is negative 1 to the 12, which is 1. Which you would also get if you wrote out all of these terms, look at their coefficients, and did the arithmetic. You get the same result. But this is a much easier way of arriving at the same thing. Yeah?
B value has a minus sign in it. Won't it be alternating and then change the value? Shouldn't we have minus 1?
But then the coefficient would be negative, right? That's like just saying, what if this was negative? Well, then the sum would be negative 14 instead, right?
Oh.
Do you see what I mean by that?
Yeah.
So any questions with this idea? So the TLDR of this, let all variables be 1. Okay? I personally think it's pretty cool, right? You have these very large random looking coefficients, and it happens to be the case that they all add up to 1, right? This, and then whatever the next one is, right? 12 choose 2 times 3 to the 10 times negative 4 squared. Sum all of those such coefficients, the sum ends up being 1. Any questions with this? Great. So another thing that we can do now with the Pascal's triangle, with the binomial theorem, Before, I think last class, we gave a combinatorial proof that the sum of the nth row of Pascal's triangle is 2 to the n. Right? What I mean by that is, before we did a combinatorial proof of this. Right? We did this on Thursday. Can anyone think of how we could use the binomial theorem to also prove the same thing? How could we use the binomial theorem to prove the same thing? Okay, let's take a look, right? The expansion of x plus y to the n is this exactly, right? Well, what if we let both x and y be 1? Then on the left-hand side, we have 1 plus 1 to the n, which would be 2 to the n. And on the right-hand side, we just have the sum of all of the terms of the form n choose k. Right, so let's just say let x equal y equal 1. Then on the left-hand side, we have 1 plus 1 to the n. And over here, we just have this sum, which is just what we're looking for. And we're done. So we prove the exact same thing, but now using the binomial theorem. So any questions with this? No? Okay. So we'll get to this, but I want to do a slightly more interesting example first. I think this is probably the coolest application of the binomial theorem. Okay, we know n choose k is only defined when n and k are whole numbers, right? And when n is greater than or equal to k. And that's because we need factorials, right? Because n choose k, n factorial over k factorial, n minus k factorial. Right? But if we could rewrite n choose k to not use any factorials, then we could technically substitute in negative numbers or other non-integers, so like decimals, for example, in as either n or k. Well, in this case, we're really looking at n. And so what do I mean by that? Well, n choose 0 is 1 no matter what n is. Is that clear? And similarly, n choose 1 is n no matter what n is. N choose 2, how can I rewrite n choose 2 to not use any factorials? Well, let's try. I have n factorial over 2 factorial, n minus 2 factorial, but then I can rewrite the numerator, as n times n minus 1 times n minus 2 factorial. Those go away, and I'm left with n minus 1 over 2. Is that clear? I could do a similar thing for n choose 3. Skip the steps, but it'll look something like n minus 1, n minus 2 over 3 factorial, which is 6. Okay? And so sure, something like 1/2 choose 3 is not really defined with our regular definition, but there's nothing stopping me from passing 1/2 into this expression for n. And I could compute a number from that. Is that clear? Okay. And so the question is, where am I going with this? Suppose we wanted to compute something like the square root of 9.02 to like 3 decimal place precision, manually, without a calculator. Can anyone see how I could use the binomial theorem and what we just talked about to help me? Any ideas? Well, so the first step, I'll probably rewrite this as 9.02 to the 1/2. But then I'll write 9.02 as 9 plus 0.02. And so what we'll do is essentially just look at the binomial expansion with x being 9, y being 0.02, and n being 1/2. But there's a potential problem here. Suppose we fix n. Suppose our exponent was 100. There's only 101 possible terms I could look at, right? I could look at n choose 0, n choose 1, n choose 2, all the way until n choose 100. Is that clear? But if n is no longer an integer or a whole number, I could theoretically look at infinitely many of these. You see what I mean? Because the definition of factorial is just multiply n by all of the integers between it and 1 inclusive. Right? But that definition doesn't really carry over to when n is not an integer. And so that's why this is an approximation. And so let's just work out the example. So what I want to do is estimate the square root of 9.02 to a couple decimal place precision. Okay? And so let's just look at the binomial expansion of this. Okay? This would be something like n choose 0, 9 to the n, plus n choose 1, 9 to the n minus 1, 0.02 to the 1, plus n choose 2, 9 to the n minus 2, 0.02 squared. And let's just use those three terms. We could actually continue this on to infinity, right? Because this this new definition of choosing doesn't have an end. I could come up, if I wanted to, with the definition of n choose 10,000, right? And that would just be the product n minus 1, n minus 2, n minus 9999 over 10,000 factorial. And I can pass in a decimal into that, and it's it will have meaning. Do you see what I mean by that? The fact that we could continue this sum on to infinity, whereas if n was in like a positive integer, we can't. Okay, cool. And so what I can actually do now is use our new definitions of n choose 0, not new, but rewritten definitions of n choose 0, n choose 1, and n choose 2, and get an expression that will evaluate to the square root of 9.02. And remember, we've chosen just to use the first three terms. Okay, what's something that you might have learned in high school that this reminds you of almost? Taylor expansion, right? Just like the Taylor expansion, you could choose to use, 100 terms, right? To the 100th, you use the 100th derivative, for example. You can choose to use as many terms as you want here. Does that kind of make sense? Okay. And you can see the similarities there as well, right? Because on the denominators, we have 2 factorial, 3 factorial. So there are a lot of similarities between what you would have seen in the Taylor expansion and this. Okay, but for example, n choose 0 will be 1. 9 to the n is just 9 to the 1/2, which is the square root of 9, which you'd expect to be our starting point, right? Then n choose 1 is really just n. 9 to the n minus 1 is 9 to the negative 1/2, right? And which is just 1 over 9 to the half. And then we have times 0.02 plus n choose 2 now, which we'll just define to be 1/2 times negative 1/2 over 2. 9 to the negative 3/2, 0.02 squared. Okay, and we could clean things up a little. We'd have 3 plus 1/2 times 3 times 0.02. Right, and then I believe this becomes 0.03. Right, and then we have minus 1/8, and then what's 9 to the negative 3/2? Something like this, 1 over 27 times 0.02 squared, whatever that is. You can put that into the calculator, and you'll see just with using 3 terms, it'll be very, very close to the true value of the square root of 9.02. Okay? This is very, very similar to using a Taylor expansion. And one of the 3 questions we'll say that'll be on the homework this week will just basically be doing this. So any questions with this? I think this is probably the coolest application of the binomial theorem because up until this point, all we talked about was counting and that sort of thing, but you can also use it for things like this. Yeah.
Can you explain how binomial theorem or this approximation can be related to any CS application you might be using something like theory or whatever?
What we can do is do this proof, which is actually related to things you'll see in future courses. Okay. Also, in future classes, you'll learn about something called the binomial distribution, which very similar to what we're seeing. Okay. So, the freshman's dream identity on its own states something like x plus y to the n is x to the n plus y to the n, which is really only true when n is equal to 1. Right? But it turns out, if you work in modulo p, where P is a prime, it actually holds true. Okay? So x plus y quantity to the P is equivalent to x to the P plus y to the P modulo P when P is prime. So can you think of how you could use the binomial theorem to help you prove this? So I'll give you a couple minutes to discuss that, and then we'll look at how you can use the binomial theorem to prove this. Okay, so any ideas on how we could use the binomial theorem to help us prove this statement when P is prime? Sure. Good. So what you're saying is when I expand out x plus y to the exponent P, every term other than the very first one and very last one will be a multiple of P. Okay? And so again, this will look something like P choose 0, which I can just write as being 1, x to the P, P choose 1, x to the P minus 1, y, P choose 2, okay. Great. So if we can somehow show that each of these terms is a multiple of P, we're good, because then modulo P, those become 0. And so what this really boils down to is we need to show that P choose I is equivalent to 0 mod P, when I is 1, 2, dot, 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 10, P minus 1. So when I is anything other than 0 or P. So any ideas on how we could show that? We need to show P choose I is a multiple of P anytime I is not equal to 0 or P. Any ideas? Yeah. Okay, so why don't we look at that? Let's see, we're going over here. We look at the expansion of P choose I, P factorial, I factorial, P minus I factorial. Great. Okay.
The first term in that is always going to be, so you pull the P out of it.
Okay.
And then have T minus 1 factorial on top.
Okay.
And then the whole thing is a
Okay, but how do we know there's not a multiple of P in the denominator? Right, good. So here we see immediately there's a multiple of P in the numerator, but that doesn't mean we can immediately say that the whole thing is a multiple of P, right? Because what if there was a multiple of P in the denominator, the two might cancel out and the thing wouldn't be a multiple of P. So what we just need to justify to ourselves is that the denominator does not contain a multiple of p. And in this case, that's relatively easy to do because p is prime. That means no integer less than it can be a multiple of it. Or it can even have a factor of p. Is that clear? Like there's not going to be anything in the denominator that is a factor of p, which would cause us to divide out the factor of p. Is that clear? So the numerator is multiple of p. And since p is prime, the denominator contains no factor or multiple of p, because every number in the denominator is strictly less than p. So it can't possibly be a multiple because it's less than p, and it can't be a factor because p is prime. So therefore, we're not going to divide out this multiple of p. And so that implies, what am I doing over here? That implies that p choose I will be equal to Cp for some c in the positive integers. And now that that's true, we know that each of these terms over here, i.e. all of the terms other than x to the p and y to the p, when we're looking at this modulo p, become 0 because they all contain a multiple of p. So they all drop out, and the only terms we're left with are x to the p and y to the p. And so that's the proof of that. Any questions with this? Okay, so that's it for today. I'll post the quiz and the quiz solutions later today. And I'll make a post on Piazza once the homework is out. Okay, and remember, the homework will be due this Sunday.